Hello everyone and welcome to this video. Today we will continue talking about the physical properties of periodic table, and specifically we will talk about melting points and electrical conductivity. So before we start studying the periodic pattern of melting points and electrical conductivity, we need to know that metals are presented on the left side of the periodic table and non-metals are presented in the right side of the periodic table. Between metals and non-metals, there are the metalloids, which are here presented in the yellow color. Metals usually metal atoms are holding together through what we call the metallic bond. The metallic bond is the factor that affects my metallic points and electrical conductivity. If I increase the strength of my metallic bond, I expect my melting points and electric conductivity to increase, because the metallic bond is holding the atoms together tightly, so I need more energy to remove to melt my lattice, because I need to remove atoms from each other, and the electrical conductivity would increase because increasing the metallic bond would increase the number of electrons shared between the ions. Now, the metallic bond, the forces that holds my atoms together, usually form what we call giant lattice. I have the metal ions surrounded by the valence electrons of each ion, and in here you could see if I increase the valence electrons, I expect my metallic bond to increase. So if I looked at the trend of the metallic bond strength in the period number 3, I have metals which are sodium, magnesium, and aluminum. I have only one valence electron. In case of sodium, I'm increasing the number of electrons, valence electrons in case of magnesium, and in case of aluminum, I have 3 electrons. So you could see that I'm increasing the valence electrons, and I'm increasing also the metallic bond, because now the sea of electrons that surrounding my ions are more. So this would make the melting points increase, and the electric conductivity increases as well. The reason behind that, now the crystal lattice are holding together through a lot of a big number of electrons, comparing in case of sodium, and this would increase it in case of aluminum. And the electric conductivity means how many electrons are free or mobile to transfer the electric charge between the electrons. If I have too many electrons to transfer, too many mobile electrons, because those are the mobile electrons, the valence electrons in case of the metallic bond are mobile. This is why I'm increasing the mobility, the number of mobile electrons. This is why I'm increasing also the electrical conductivity. But let's look at silicon. Have this giant lattice, and this giant lattice are holding my atoms together through a strong covalent bond. This is why I could see in here, although silicon is a metalloid, not metals, but still it has this strong covalent bond that holding my lattice together, and it is making a large giant molecule. This is why this giant molecule would just need more energy to enable us to melt the silicon. So you could see that silicon has the highest melting point comparing to metals and non-metals. Now, moving to this large drop between the metalloids and non-metals, you could see non-metals would have the least melting points, due to the fact that I have now small molecules holding together through the covalent bond, because I have a small molecules in case of phosphorus. I have the tetrahedral structure. I have only 4 atoms holding together. This is why you have this higher melting point of sulfur, because it has 8 electrons holding together. So you could see in here I have more atoms holding together. So those more atoms holding together will make the melting point of sulfur little bit higher than phosphorus. And if we looked at chlorine molecule and argon, you could see in case of chlorine there are only 2 atoms holding together. This is why I expect the melting point to be very low in case of chlorine, and the argon I have only 1 atom, so my molecule contains only 1 atom. This is why I have the least melting point. Now if I looked at again at this graph and I looked at the melting points, you could see it in here, the values in this table. It is actually increasing because I'm increasing the atomic the metallic bond, and I'm increasing the number of electrons. This is why my metallic bond is increasing and they become stronger. In silicon, it is a covalent bond, but it is arranged in crystals that make it so tight together that it is very hard to break down silicon molecules. Now, phosphorus have only tetrahedral structures. This is why it have less melting point than silicon and sulfur. Sulfur, I have sulfur molecule with 8 atoms, where in phosphorus I have only 4 atoms. So in sulfur I have 8 atoms bonding together, but in phosphorus I have only 4 bonding together. In chlorine I have 2, and in argon I have 1. This is why it have very low melting points. Now, if I looked at the electric conductivity, if I have 1 electron moving, the sea of electrons will be reasonable. This sea of electrons will conduct electricity. But if I have 2 electrons, I will have even more electric conductivity. 3 electrons, more electric conductivity. But you have to remember, silicon is one of the metalloids. This is why it have a lower electric conductivity comparing to the whole the bonded together in here. So you have to remember one thing: in silicon you don't have this sea of free electrons like in metallic bond. So those are metals. You have a sea of electrons moving the electric current, but in silicon you have covalent bond. This is why you don't have mobile electrons to conduct electricity. This is why the electricity is way lower than in case of metals, but it is reasonably higher than the not metals. You have to remember one thing: silicon is actually metalloid. Now for the phosphorus sulfur, this very low very low electrical conductivity due to the lone pair on phosphorus and sulfur. Chlorine and argon doesn't have any conductivity at all. The reason behind that, they are non-metals, and those non-metals are holding together through the covalent bond, which means all electrons are already bonded or busy in a covalent bond and doesn't have any chance to do to conduct electricity. Now, period number 3, if I looked at the bond, in here I have metallic bond, metallic bond, metallic bond. In here I have covalent bond, and this is why we could explain the electric conductivity according to the bond. If I have metallic bond, I have electric conductivity. Now, moving to the covalent bond, I will not have electric conductivity. You have to remember, argon is a noble gas. Argon atoms are presented by itself, so you have only 1 atom. It doesn't bond to any other atoms. Now the molecule of argon is only 1 atom. So the structure in here, I have giant metallic lattice. Even in magnesium and aluminum, this giant crystal lattice will be hold it together stronger, but in silicon I have giant molecule. And now I'm moving to the non-metals, where I have simpler types of molecules. Now moving to the first ionization energies and the pattern in the we will also explain the pattern of first ionization energy. in period number 3. So in period number 3, what you have, first you have sodium with 11 electrons, and it has this one valence electron outermost in the outermost shell. It is very easy to remove this electron. In magnesium, you have 2 electrons which you can move, but in aluminium, it even have less ionization energy comparing to magnesium. The reason behind that, because it loses first the 1 electron in the p orbital before losing the 2 electrons in the s orbital. This is why aluminium has a lower ionization energy than in case of magnesium. Magnesium, you have to break a filled orbital, which is the s orbital, but aluminium already have only 1 electron. It is easier to lose this electron. Now moving to silicon, you are increasing the ionization energy, and the reason behind that, actually non-metals tends to gain electrons, not to lose electrons. So it is very hard to take out 1 electron from their outermost shell. This is why you could see that you are increasing the ionization energy of the first ionization energy, but you could see this drop between the sulfur and the phosphorus, and the reason behind that is actually in phosphorus has a higher ionization energy because you are taking 3 electrons. The 3 electrons is not paired, but in here I have 4 electrons, and 4 electrons, one of them are paired electron. This is why it is easier to remove first this electron, which is in the opposite direction, then we move the rest of the parallel electrons. So the reason behind this drop is actually the pairing of electrons in case of sulfur, while in phosphorus the 3 electrons are non-paired electrons. So by that we came to the end of part 2. In the next video we'll start talking about the periodicity of the chemical properties. Until next video, thank you and goodbye.